So, good morning. I am Chef Iver Refrea, and today I'll be discussing and demonstrating experiment theory of Kirchhoff's laws. So, as stated here in the lab report. So, before I discuss the general overview of the lab report, we must first discuss the brief concepts. We must first discuss briefly about the concepts regarding or behind the lab experiments, which are Kirchhoff's laws. So, first off is Kirchhoff's current law. So the Kirchhoff's current law, or KCL, is the first law that details with the conservation of charge entering and leaving a junction. So to determine the amount or magnitude of the electrical current flowing around an electrical or electronic circuit, we need to use certain laws or rules that allows us to write down these currents in the form of an equation. These network equations used are those according to Kirchhoff's laws, and as we are dealing with circuits, currents will as we're dealing with circuit currents, we will be looking at Kirchhoff's current law or KCL. So Kirchhoff's current law is one of the fundamental laws used for circuit analysis. His current law states that for a parallel path, that the for a parallel path, the total current entering a circuit's junction is exactly equal to the amount is exactly equal to the total current leaving the same junction. This is because it has no other place to go as no charge is lost. In other words, the algebraic sum of all the currents entering and leaving a junction must be equal to zero, as the summation of in equals the summation of out. So this idea by Kirchhoff is commonly known as the conservation of charge, as the current is conserved around the junction with no loss of current. So that is Kirchhoff's current law. So the second part is the Kirchhoff's voltage law. This is the second law that deals with the conservation of energy around a closed circuit path. So Kirchhoff's voltage law is the second of his fundamental laws, which we can use for circuit analysis. His voltage law states that for a closed loop series path, the algebraic sum of all voltages around any closed loop in a circuit is equal to zero. This is because a circuit loop is closed conducting path, so no energy is lost. In other words, the algebraic sum of all the potential differences around the loop must be equal to zero, as the summation of V equals zero. So note here that the algebraic sum means to take into account the polarities and signs of the sources and voltage drops around the loop. This idea by Kirchhoff is commonly known as the conservation of energy. As moving around a closed loop or circuit, you will end up back to where you started in the circuit, and therefore back to the same initial potential with no loss of voltage around the loop. Hence, any voltage drops around the loop must be equal to any voltage sources met along the way. So when applying Kirchhoff's voltage law to a specific circuit element, it is important that we pay special attention to the algebraic signs, positive, negative, or plus or minus, of the voltage drops across elements and the EMF sources. Otherwise, our calculations may be wrong. So that is about KVL or Kirchhoff's voltage law. So I will now go to Tina Pro to show you my work on E3, on experiment 3. So there. So as you can see, this is my complete setup for experiment 3. So I'm sorry. So before that, we must first discuss the uh original circuit or setup as given by our professor. So this is the first set. So this is the original setup. So the volt. So the volt for voltage for the switch, it should have 15 volts. For resistor 1, it should have 200 ohms. For resistor 2, there should be 550 ohms. For resistor 3, there should have been 500 ohms. For resistor 4, there should have been 350 ohms, and resistor 5 is 600 ohms respectively. So going back to Tina Pro. So here, so from basing from the setup, there are a total of 5 setups for each resistor and a switch. So there are 4 components: the switch, the voltmeter, the ammeter, and the resistor. So there are 4 primary components. So, as stated in the experiment, in the first setup, it's 15 volts for the switch here. For the first one right here, there's the second one, the second part. the third region, the fourth region, and the fifth region. So let's go to the first region. So when we find out the values by pressing this button, so you can see that for 200 ohms, the first one, the current is 13.92 milliamperes, while the voltage is 2.78 volts. For the second resistor, which is 550 ohms, the value for the voltmeter is 7.66 volts, while the value for the ammeter is 13.92, as same as the first one. For the third one, for the 500 ohm resistor, the value for the ammeter is 9.12 milliamperes, while the voltage is 4.56 volts, as stated here. For the fourth one here, if the resistor is 350 ohms, so the value for the ammeter is 4.8 milliamperes. Then for the voltmeter, which is 1.68 volts. And lastly, for this part, for 600 ohm, the resistor 5, the ammeter value for the ammeter is 4.8 milliamperes, while the voltmeter is 2.88 volts. So going back to the experiment as stated here, so the values are corresponding and properly placed. And this is the screenshot of the complete experiment as discussed earlier by me, which I have shown in TinaPro. And this is the second portion of the experiment, which is the values and solutions. So you can see for the first value, the value, so the formula is negative VS1 plus the voltage for R1, voltage for R4, and voltage for R2 resistors. So it should equate to 0 as stated here. So the first one is negative 15 volts, because as stated here, it should be negative 15 as stated in the negative sign, plus 2.78 volts as stated by the voltage for resistor 1 here, plus VR4, which is VR4 is 1.68 as stated here, plus VR2, which is 7.66. Adding all that up, it should have equal to 0. Next is this one, the second item. So the formula is negative VS1 plus the voltage for resistor 1 plus voltage for resistor 3 and voltage for resistor 2 should equal to 0 once again. So as stated here, negative 15 volts plus VR1 take a plus 2.78 plus VR3, which is 4.56 stated here, plus VR2, which is 7.66 as stated here. So as you can see, adding all, performing the equation, it should equal to 0. And for the third item, stated here, the formula is negative voltage R for resistor 3, voltage for resistor 4, and voltage for resistor 5 should equal to 0 once again. So looking back, so VR3 is negative 4.56 here, added by the negative sign, plus 1.68 volts as stated for VR4. VR4 right here, and 2.88 for VR5 as stated here. VR5, there, VR5. Adding all that up should equal to once again 0 volts, following Kirchhoff's voltage law. So lastly is for the Kirchhoff's current law. Here is for I1 minus I3 minus I4 equal to 0. So 13.92 for I1, which is 13.92 milliamperes, minus 9.12 milliamperes as I3 for I3, minus 4.8 milliamperes for I4, which is stated here. So performing the equation, it should equal to 0 milliampere. So that is the first part of so that is the first part for module 1 exam. So thank you very much, and I hope you enjoyed.